We are going to continue our discussion of sequences in mathematical induction and recursion with sections 2 through 4 today. Should be a long day. Mathematical induction part 1, proving formulas. In natural science courses, deduction and induction are presented as alternative modes of thought. Deduction being to infer a conclusion from general principles using laws of logical reasoning, and induction being to enunciate a general principle after observing it to hold in a large number of specific instances. Discovery of new mathematical facts often occurs through experimentation with examples, but mathematical induction as a proof is not inductive, but deductive. Once proved by mathematical induction, a theorem is known just as certainly as if it were proved by any other mathematical method. So the principle of mathematical induction is done this way, or is shown this way. Let P of n be a property that is defined for integers n, and let a be a fixed integer. Suppose the following two statements are true. P of a is true, and 2 for every integer k greater than or equal to a. If P of k is true, then P of k plus 1 is true. Then the statement for every integer n greater than or equal to a, P of n is true. The first use of mathematical induction occurs in the work of an Italian scientist, whose name I'm not sure I know how to pronounce. And in 1653, Mr. Pascal gave a clear description of the technique. In 1883, De Morgan, who is known for De Morgan's laws, gave the process the name mathematical induction. An equivalent logical inference rule, also known as is known as the well-ordering principle. To visualize the idea of mathematical induction, imagine an infinite collection of dominoes positioned one behind the other in such a way that if any given domino falls backward, it makes the one behind it fall backward as well. Then imagine the first domino falls backward. What happens? Well, they all fall down eventually. If the kth domino falls backward, it pushes the k plus 1 domino backward as well. To see the connection between this image and the principle of mathematical induction, let P of n be the sentence, the nth domino falls backwards. It is given that for each k greater than or equal to 1, if P of k is true, then P of k plus 1 is also true. It is also given that P of 1 is true, the first domino falls. Thus, by the principle of mathematical induction, P of n, the nth domino falls backward, is true for every integer n greater than or equal to 1. Proving a statement by mathematical induction is a two-step process. The first step is called the basis step. The second step is called the inductive step. Consider the statement of the form for every integer n greater than a or equal to a property P of n is true. To prove such a statement, perform the following two steps. The first step, the basis step, show that P of a is true. The inductive step, show that for the second step, show that for every integer k greater than or equal to a, if P of k is true, then P of k plus 1 is also true. To perform this step, suppose that P of k is true, where k is any particular but arbitrarily chosen integer with k greater than or equal to a. This supposition is called the inductive hypothesis. Then show that p of k plus 1 is true. So you use mathematical induction to prove that 1 plus 2 plus 3 plus 4, etc. to plus n equals n times n plus 1 over 2 for every integer n greater than or equal to 1. Well, to construct a proof by induction, you must first identify the property. In this case, it's the equation. The proof will show that the equation is true for every integer greater than or equal to 1. In the basis step of the proof, you must show that the property is true for n equals 1. Or in other words, that p of 1 is true. Now, p of 1 is obtained by substituting 1 in place of n in p of n. The left-hand side of the equation, p of n is the sum of all successive integers starting from 1 and ending at 1, which is just 1. To write p of 1, just copy p of n and replace it with each n by replace each n with 1. Thus, p of 1 is 1 times 1 plus 1 over 2. Of course, this equation is true because the right-hand side is 2 over 2, or 1, which equals the left-hand side. In the inductive step, you assume that p of k is true for a particular arbitrarily chosen integer k. This assumption is the inductive hypothesis. You must then show that p of k plus 1 is true. What are p of k and p of k plus 1? P of k is obtained by substituting k for every n in p of n. Similarly, p of k plus 1 is obtained by substituting the quantity k plus 1 for every n that appears in p of n. Thus, p of k plus 1 is given here, which ends up being this here when you simplify. Now, the inductive hypothesis is the supposition that p of k is true. How can this supposition be used to show that p of k plus 1 is true? P of k plus 1 is an equation, and the truth of an equation can be shown in a variety of ways. One of the most straightforward is to use the inductive hypothesis along with algebra and other known facts to separately transform the left-hand side and the right-hand side until you see that they are the same. In this case, the left-hand side of p of k plus 1 is 1 plus 2 plus 3, etc. to plus k plus 1, which equals 1 plus 2 plus 3, etc. to plus k plus 1. By substitution from the inductive hypothesis, you can say that 1 plus 2 plus 3, etc. to plus k can be substituted with k times k plus 1 over 2, and then add that to k plus 1. Then you can do some algebraic tap dancing and get to k squared plus 3k plus 2 over 2. So the left-hand side of p of k plus 1 is k squared plus 3k plus 2 over 2. Now the right-hand side of p of k plus 1 is k plus 1 times k plus 2, which is equal to k squared plus 3k plus 2 by multiplying out the numerator. Thus, the two sides of p of k plus 1 are equal to each other, and so the equation p of k plus 1 is true. So, the sum of the first n integers is equal to n times n plus 1 all over 2. If a sum is definition here, if a sum is, with a variable number of terms is shown to equal an expression that does not contain either an ellipsis or a summation symbol, we say that the sum is written in closed form. So, using that formula for the sum of first n integers, evaluate these. Well, that would be 2 times n times n plus 1 all over 2 with n equaling 250, because you could factor out the 2 in A, make it 1 through 250 instead of just the even numbers. You can evaluate the second one by taking the sum of 1 through 50 and subtract the sum of 1 through 4. And C, like I said, factoring out the 2 and making n 250 gives you 62,750. And then here, do the first 50 integers and then positive integers and subtract 1 through 4. And then substitution for h minus 1 for n, and you get this here. Another famous and important formula in mathematics, the formula for the sum of a geometric sequence. In a geometric sequence, each term is obtained from the preceding one by multiplying by a constant factor. If the first term is 1 and the constant factor is r, then the sequence is 1, r, r squared, r cubed, etc. to rn, to the n. The sum of the first n terms of the sequence is given by the formula here. The summation is equal to r to the n plus 1 minus 1 over r minus 1 for every integer n greater than or equal to 0 and every real number r not equal to 1. The expanded formula of the formula is given here. But because r to the 0 is 1 and r to the 1 is r, the formula for n greater than or equal to 1 can be written like so. In some mathematical contexts, 0 to the 0 is regarded as indeterminate. In discrete mathematics, we usually define 0 to the 0th power as 1 being equal to 1. So that when we do the summation of I to 0 is from 0 to n, r to the I, we do not give special attention to the case of r equals 0. Prove that the sum of a geometric sequence is equal to this formula for every integer n greater than 0 and every real number r except 1. In this example, the property P of n is again the equation, although in this case it contains a real variable r. Because r can be any real number other than 1, the proof begins by supposing that r is a particular but arbitrarily chosen real number not equal to 1. Then the proof continues by mathematical induction on n, starting with n equals 0. In the basis step, you must show that P of 0 is true. That is, you show that the property is true for n equals 0. So you substitute 0 for each n in P of n. In the inductive step, you suppose k is any integer with k greater than or equal to 0, for which P of k is true. That is, you suppose the property is true for n equals k. So you can substitute k for each n in P of n to get the inductive hypothesis. Then you show that P of k plus 1 is true. That is, you show that the property is true for n equals k to the n equals k plus 1, and substitute k plus 1 for each n in P of n, or which is this equation here is what you're trying to show. Now the sum of a geometric sequence is given here. Proving an equality. Proofs of the basis and inductive steps illustrate two different ways to show that an equation is true. Transforming the left-hand side and the right-hand side independently until they are seen to be equal. And 2, transforming one side of the equation until it is seen to be the same as the other side of the equation. Sometimes people use a method they believe proves the equality but is actually invalid. For example, to prove the basis step for theorem 522, they perform the following steps. Is that the case? Is that a valid manipulation? No. Now you would actually do the math and make 0 there and then 0 here, and then do the math. 1 minus 1. No. Deducing additional formulas. The formula for the sum of a geometric sequence can be thought of as a family of different formulas in R for each real number R except 1. In each of A and B below, assume that M is an integer that is greater than or equal to 3. Write each of the sums in closed form. Yeah? It would be by applying the formula for the sum of a geometric sequence. Simple substitution for the 3 as is equal to R, and M is variable. You get 3 to the M minus 1 all over 2. And in the second one, you can factor out the 3 squared, the first term, to get that to equal to 1. And 3 for the second term, and 3 squared for the third term, all the way up to M minus 2. And 3 to the M minus 2. And by part A, you can say that the result is 9 times 3 to the M minus 1 all over 2. As with the formula for the sum of the first n integers, there's a way to think of the formula for the sum of the terms of a geometric sequence that makes it simple and intuitive. Let S sub n equal the sum of the geometric sequence. Let R times S sub n be the R plus R squared plus R cubed, etc., to R plus 1, or to the n plus 1. And then you can subtract S sub n from that, from both sides, and you get R times R to the n plus 1 minus 1. Then divide both sides by uh, 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 oh, and then by the by substitution, you get R minus 1 times S sub n equals R times S sub n minus S sub n. Equating the right-hand sides of the equation and dividing by R minus 1, you get S sub n equals R to the n plus 1 minus 1 all over R minus 1. And that is it for that section. All right. Next section is Mathematical Induction Part 2, Applications. In this section, we'll show how to apply it to a broader variety of situations. As a first example, consider the argument that the US penny should be eliminated because it isn't profitable to produce. Due to inflation and the rising cost of metals, it actually costs more than 1 cent to produce a penny. If the penny were eliminated and another coin worth 3 cents were introduced, what prices could be paid using only 3 and 5 cent coins? Well, here's some examples. Others are possible as well, but for every proposition, for every integer n greater than or equal to 8, n cents can be obtained using 3 cent and 5 cent coins. Well, use mathematical induction to prove that for each integer, well, this is a divisibility property here. Use mathematical induction to prove that for each integer n greater than or equal to 0, 2 to the 2n minus 1 is divisible by 3. As in the previous proofs, by mathematical induction, you need to identify P of n. In this example, P of n is the sentence 2 to the 2n minus 1 is divisible by 3. By substitution, the statement for the basis step P of 0 is 2 to the 2 times 0 minus 1 is divisible by 3. So this inductive step, the supposition for it is 2 to the 2k minus 1 is divisible by 3. So that's the inductive hypothesis. And the conclusion to be shown is that 2 to the 2k minus 1 is divisible by 3. And then the conclusion to be shown is 2 to the 2k plus 1 minus 1 is divisible by 3. Recall that any integer m is divisible by 3 if and only if m equals 3r for some integer r. Now the statement p of 0 is true because 2 to the 2 times 0 is minus 1 is 2 to the 0, or 1, minus 1 equals 0, which is divisible by 3. Prove the inductive step, you suppose that k is any integer greater than or equal to 0, such that p of k is true. In other words, you suppose that 2 to the 2k plus or minus 1 is divisible by 3. You must then prove the truth of p of k plus 1. Thus, you must show that 2 to the 2k plus 1 minus 1 is divisible by 3. Now, 2 to the 2k plus 1 is equal to 2 to the 2k times 2 to the second minus 1, or 2 to the 2k times 4 minus 1. Your aim is to show that 2 to the 2k times 4 minus 1 is divisible by 3. But why would that be the case? Both 2 to the 2k times 4 minus 1 and 2 to the 2k minus 1 have a lot in common, and by the inductive hypothesis, 2 to the 2k minus 1 is divisible by 3. Now, see what happens when you subtract 2 to the 2k minus 1 from 2 to the 2k times 4 minus 1. You get 2 to the 2k times 3, which is divisible by 3 because it is some integer. It is some integer times 3. This is true by the inductive hypothesis. So, adding this quantity to both sides, you have this term which is divisible by 3 and this term divisible by 3. And since the sum of two terms that are divisible by 3 is divisible by 3, the left-hand side is divisible by 3. So, within that is what it was to be shown. So 2 to the 2n minus 1 is divisible by 3. Use mathematical induction to prove that for each integer n greater than 3, this one. I'm going to skip over this example because it's full of typos. It's supposed to be 2n, not 2 to the n. There. They get it right here, and then they get back to doing the exponents weird, and it's kind of hard to follow the typos in the slides. So I'm going to skip over that. And then back to at the end, they're back at 2n instead of 2 to the n. So they need to do better with their proofreading. Anyway, so proving a property of a sequence. Define a sequence A as follows. A sub 1 equals 2. A sub k equals 5a to sub k minus 1 for every integer k greater than or equal to 2. Write the first 4 terms of the sequence. It is claimed that for each integer n greater than 0, the nth term of the sequence has the same value as that given by the formula 2 times 5 to the n minus 1. So the claim is that sequence satisfies the equation a sub n equals 2 times 5 n to the n minus 1. So those are the first four terms. Just multiplied out. Use mathematical induction to show that every term of the sequence satisfies the equation. Begin by showing that the first term of the sequence satisfies the equation. So then suppose that an arbitrarily chosen term satisfies the equation, and prove that the next term also satisfies the equation. So, restating the problem here, and step one is to show P of 1 is true. Establish that P of 1 must show that 2 times 5 to the 1 minus 1 is equal to the first term in the sequence. And it is, because 5 to the 1 minus 1 is 2. 5 to the 1 minus 1 is 1, and 2 times 1 is 1, or is 2, so there you go. It's and that's and it's equal to A1 as defined, coming from the definition of the sequence. So the P1 are equal to the same quantity. Now show that for each integer k greater than or equal to 1, if P of k is true, then P of k plus 1 is also true. Suppose that P of k is true, let k be any integer with k greater than or equal to 1. And suppose that a sub k equals 2 times 5 to the k minus 1 is true. That's the inductive hypothesis. Show that a sub k plus 1 equals 2 times 5 to the k plus 1 minus 1. Or equivalently, a sub k plus 1 equals 2 times 5 to the k. But the left-hand side of the equation is given here by the definition. And it can be simplified to be a sub k plus 1 equals 5 times a sub k. When you substitute the inductive hypothesis, you can, and regrouping and doing the law of exponents, you see that the right-hand side of P of k plus 1 is 2 times 5 to the 5 to the k. So we've shown through inductive mathematical induction that the sequence, the formula holds true for all the sequence. A trouble with tromonos. The word polyomino, a generalization of domino, was introduced by this fellow here, and subsequently he and others have proved many interesting properties about them, and they became the basis for the popular computer game Tetris. Anybody play that still? Oh, okay. It's an old game. But anyway, a particular type of polyomino called a tromono is made up of 3 attached squares, which can be of 2 types, straight and L-shaped. Straight, yeah. Call a checkerboard that is formed by using m squares on a side an m by m checkerboard. Observe that if one square is removed from a 4x4 checkerboard, the remaining squares can be completely covered by L-shaped tromonos. For instance, a covering for one such board is illustrated here. So the theorem that they came up with, apparently using mathematical induction, was that for any integer n greater than 1, if 1 square is removed from a 2 to the n by 2 to the n checkerboard, the remaining squares can be completely covered by L-shaped tromonomes. And that is it for that slide deck. And let's see if it behaves this time. Yeah, nope, made it. Looks like this last class session too. All right. Sequences and mathematical induction and recursion. Section 4. Strong mathematical induction and the well-ordering principle for integers. A little bit of a mouthful. Strong mathematical induction is similar to ordinary mathematical induction in that it is a technique for establishing the truth of a sequence of statements about integers. Also, a proof by strong mathematical induction consists of a basis step and an inductive step. However, the basis step may contain proofs for several initial values, and in the inductive step, the truth of the predicate P of n is assumed not just for one value of n, but for all values through k. And then the truth of P of k plus 1 is proved. So, the principle of strong mathematical induction: let P of n be a property that is defined for integers n, and let a and b be fixed integers, with a being less than or equal to b. Suppose the following two statements are true. P of a plus 1, etc., P of a or P of b are all true. That's the basis step. You got to prove that. For every integer k greater than or equal to b, if P of I is true for each integer I from a through k, then P of k plus 1 is true. That's the inductive step. Then the statement for every integer n greater than or equal to a, P of n is true. So the supposition that P of I is true for each integer I from a through k is called the inductive hypothesis. So applying strong mathematical induction. Divisibility by a prime theorem states that any integer greater than 1 is divisible by a prime number. We prove this theorem using strong mathematical induction. Any integer greater than 1 is divisible by a prime number. Yeah. Well, the idea for the inductive step is this: if you're given an integer greater than 1, that is not itself prime, then it is a product of two smaller positive integers, each of which is greater than 1. By the inductive hypothesis, you are assuming that each of these smaller integers is divisible by a prime number. And so, by transitivity of divisibility, those prime numbers also divide the integer you started with. So, proof: show that P of 2 is true. State the problem first, and then show that P of 2 is true. Show that 2 is divisible by a prime number. But because it is true, because 2 is divisible by 2, and 2 is a prime number. So there you go. Now show that for every integer k greater than 2, if P of I is true for each integer from 2 through k, then P of k is true. P of k plus 1 is also true. Let k be any integer with k greater than or equal to 2. Suppose that I is divisible by a prime number for each integer I from 2 through k. There's your inductive hypothesis. Then show that k plus 1 is divisible by a prime number. Well, you have two cases here. K plus 1 is prime. In this case, k plus 1 is divisible by a prime number, namely itself. Case number 2, k plus 1 is not prime. In this case, k plus 1 equals a times b, where a and b are integers, and they are between 1 and k plus 1, because they have to be less than that, because k is not prime. Thus, in particular, 2 is greater than or less than or equal to a, which is less than or equal to k. So by the inductive hypothesis, a is divisible by a prime number. So, in addition, because k plus 1 equals a times b, we have that k plus 1 is divisible by a. Hence, k plus 1 is divisible by a, and a is divisible by p, and by transitivity of divisibility, k plus 1 is divisible by the prime number p. Therefore, regardless of whether k plus 1 is prime or not, it is divisible by a prime number. So we can conclude that this given statement is true. Okay, how about the sequence here? S sub 0 is 0, S sub 1 is 4, S sub k is 6a sub k minus 1 minus 5a sub k minus 2 for every integer greater than or equal to 2. It is claimed that for each integer n greater than or equal to 0, the nth term of the sequence has the same value as the given by the formula 5 to the n minus 1. So it's the sequence proves that the sequence satisfies the equation S sub n equals 5 to the n minus 1. So the first 4 terms are given here. Use strong mathematical induction to show that every term of the sequence satisfies the equation. The basis step shows the first 2 terms satisfy it. This is necessary because, according to the definition, computing values of the later terms requires knowing the values of the 2 previous terms. So if the basis step only shows that the first term satisfies the equation, it would not be possible to use the inductive step to deduce that the second term satisfies the equation. In the inductive step, you suppose that for any arbitrary chosen integer k greater than or equal to 1, all the terms of the sequence from s sub 0 through s sub k satisfy the given equation, and you then deduce that s sub k plus 1 must also satisfy the equation. So the proof. Find the sequence and show that P of n is true. So show that P of 0 and P of 1 are true. So S sub 0 is 5 to the 0, or 1 minus 1, or 0, which equals 0. And S sub 1 equals 5 to the 1 minus 1, which is 4, which are the values given, agree with the values given by the definition of the sequence. Now show that for every integer k greater than 1, if p of I is true for each integer I from 0 through k, then k plus 1 is also true. Let k be any integer with k greater than or equal to 1. And suppose that s sub I equals 5 to the I minus 1 for each integer I being between 0 and k. That's your inductive hypothesis. We must show that s sub k plus 1 equals 5 to the k plus 1 minus 1. But since k is greater than or equal to 1, we have that k plus 1 is greater than or equal to 2. So, by the definition, we can do some substitution. And by definition of a hypothesis, by the inductive hypothesis, that's another typo there. And then multiplying out and applying law of exponents, factoring out a 6 and doing some arithmetic. And some more arithmetic, and finally applying the law of exponents, which gives us the result which was to be shown. And so we can conclude that the given statement is true. Now for another sequence that involves the floor function. Find a sequence A as follows. A sub 1 is 0, A sub 2 is 2, A sub k equals 3A sub the floor of k over 2 plus 2 for every integer k greater than or equal to 3. Find the first 7 terms of the sequence. Prove that A sub n is even for every integer n greater than or equal to 1. Well, A sub 0, or A sub 1 is 0, A sub 2 is 2, 2, 8, 8, 8, 8. So let the property P of n be the sentence A sub n is even. We use the strong mathematical induction to show the property holds true for every integer n greater than or equal to 1. Show that P of 1 and 2 are true. They're true because by the definition, A sub 1 and A sub 2 are 0 and 2 respectively, and those are both even integers. Show that every integer k greater than 1, if P of I is true for each integer from 1 through k, then P of k plus 1 is also true. Suppose that A sub I is even for each integer I, with I being between 1 and k. That would be our inductive hypothesis. Then, by definition, A sub k equals 3A sub the floor of k minus k over 2 plus 2. Now, A sub k over 2 is even by the inductive hypothesis because because k is greater than or equal to 1, so that 1 the floor of k over 2 is between 1 and k. Thus, 3A sub k, the floor of k over 2, is even because it is a product of an even and odd number, odd and even integer, and hence 3A sub k, floor of k over 2 plus 2 is even because the sum of two even integers is even. So a sub k, which equals 3a sub floor of k over 2 plus 2 is even, as was to be shown. So we can conclude that the given statement is true. Convention. Let us agree to say that a single number x sub 1 is a product with one factor and can be computed with 0 multiplications. Prove that for any integer n greater than 1 or equal to 1, if x sub 1, 2, 3, etc. to x sub n are n numbers, then no matter how the parentheses are inserted into their product, the number of multiplications used to compute the product is n minus 1. The truth of the basis state follows immediately from the convention about a product with one factor. The inductive step is based on the fact that when several numbers are multiplied together, each step of the process involves multiplying two individual quantities. For instance, the final step for computing this here is to multiply these two quantities. Oops. In general, when k plus 1 numbers are multiplied, the two quantities in the final step each consist of fewer than k plus 1 factors. This is what makes it possible to use the inductive hypothesis. So the proof, restate the problem, or the statement to be proven. Show that p of 1 is true. Number of multiplications need to compute a product of x sub 1 is 1 minus 1. This is true because by convention, x sub 1 is a product that can be computed with 0 multiplications. And 0 equals 1 minus 1, of course. So, show that for every integer k greater than or equal to 1, if p of I is true for each integer I from 1 to through k, then p of k plus 1 is also true. So, let k be any integer, with k being greater than or equal to 1, and suppose that for each integer I from 1 through k, if x1 sub x sub 1, x sub 2, etc. to x sub I are numbers, then no matter how many parentheses are inserted into their product, the number of multiplications used to compute the product is I minus 1. That is your inductive hypothesis. We must show that if x sub 1, x sub 2, etc. to x sub k plus 1 are k plus 1 numbers, then no matter how many parentheses are inserted into their product, the number of multiplications used to compute the product is k. Consider the product of k plus 1 factors. When parentheses are inserted in order to compute the product, some multiplication is the final one, and each of the two factors making up the final multiplication is a product of fewer than k plus 1 factors. Let L be the product of the left-hand factors and R be the product of the right-hand factors. Suppose that big L is composed of little l factors and big R is composed of little r factors. Then L plus R equals k plus 1, the total number of factors in the product. And little l is less than or equal to k but greater than or equal to 1. Likewise, R is less than or equal to k and greater than or equal to 1. By inductive hypothesis, evaluating L takes little l minus 1 multiplications, and evaluating big R takes little r minus 1 multiplications. Because one final multiplication is needed to evaluate L times R, the number of multiplications needed to evaluate the product of all k plus 1 factors is k, which was to be shown. So there you go. Applying strong mathematical induction. Theorem 1, or 541. The existence and uniqueness of binary integer representation. Given any positive integer n has a unique representation in the form of this given here, where r is a non-negative integer, c sub r equals 1, c sub j equals 1 or 0 for each j from 0 through r minus 1. That doesn't go into the proof of that. Jumps right into the well-ordering principle for the integers. The well-ordering principle for the integers looks very different from both the ordinary and the strong principles of mathematical induction, but it can be shown that all three principles are equivalent. In other words, if any one of the three is true, then so are both of the others. The well-ordering principle for the integers. Let S be a set of integers containing one or more integers, all of which are greater than some fixed integer. Then S has a least element, a smallest element. Just mathematically formulating a way of saying something that's basically common sense. If you have a group of numbers, there's going to be a smallest one. Yeah, but you have to have a group of integers, and there has to be at least one in the group, and then one of them is going to be the smallest element. Like I said, a lot of this class is formalizing common sense. In each case, if the set has the least element, state what it is. If not, explain why the well-ordering principle is not violated. The set of all positive real numbers. Is the well-ordering principle violated? What's the smallest positive real number? That's an integer, not a real number. So it's not violated. There is no smallest, because you could always take a real number and divide it by 2 and get a smaller one. So there is no value, but it doesn't violate the well-ordering principle because they're real numbers, not integers. The well-ordering principle only applies to integers. The set of all non-negative integers n such that n squared is less than n. There is no n, so it's an empty set. There is no positive. There's no non-negative integers n such that n squared is less than n. There aren't any. So there is no least value, but the well-ordering principle is not violated because the well-ordering principle requires there to be at least one element in the set. And there is no element in that set, so there you go. The set of all non-negative integers of the form 46 minus 7k, where k is an integer. Well, 7k, to get a non-negative integer from 46 minus 7k, you can go 46 minus 7 with k equals 1. 47 minus 14, or 46 minus 14 with k equals 2. And to keep them non-negative, you could go k equals 6, right? 46 minus 7 times 6, which is 42, so you'd get 4. So that would be the smallest non-negative integer of that form. So there is no least positive real number. For if x is any positive real number, then x divided by 2 is a positive real number that is less than x. No violation, because it only applies to integers. There is no least non-negative integer that n such that n squared is less than n, because there is no non-negative integer that satisfies this inequality. Not violated because the principle only applies to sets that contain at least one element. Tables shows you the values of 46 minus 7k for various values of k. The smallest non-negative is 4. So yeah. Quotient remainder theorem. Existence part. Given any integer n and any positive integer d, there exists integers q and r such that n equals dq plus r, and r is between 0 and d. And that would be it. That's why they threw the quotient remainder theorem in there. I mean, that was last chapter that we covered the quotient remainder theorem, so I don't know why they threw this in here again. They didn't give any context or anything like that. So, but anyway, that's the end of this slide deck, and that'll be it for the day. Have a good weekend. See you on Tuesday, and enjoy the beautiful weather.